January 21, 1943. Casablanca, Morocco. American and British leaders formally approved the combined bomber offensive, committing U.S. Army Air Force's heavy bombers to sustained daylight operations against Germany, with the explicit requirement that German air defenses be reduced as a prerequisite for any later invasion of Western Europe. U.S. planners did not treat German air defense as a single obstacle but as an interconnected system composed of early warning, fighter control, interceptor aircraft, flak units, fuel supply, and industrial replacement capacity. This analytical framing emerged from pre-war air war plans division studies and was refined by operational experience over occupied Europe in 1942. The 8th Air Force adopted a systems analysis approach that identified leverage points where bomber pressure could produce cascading effects. Intelligence officers mapped radar stations, sector control centers, fighter bases, aircraft factories, and fuel infrastructure as nodes, whose degradation would force the Luftwaffe to react in predictable, costly ways. Rather than prioritizing city destruction, American doctrine emphasized engaging the enemy's defensive response. Daylight precision bombing was selected specifically because it compelled German fighters to intercept, exposing pilots, aircraft, and command structures to attrition. This choice deliberately contrasted with British night bombing, which avoided fighters but left the defensive system largely intact. By mid-1943, U.S. target lists increasingly reflected this logic. Aircraft assembly plants, engine factories, ball-bearing facilities, and later synthetic fuel plants were selected not for symbolic value but because they constrained the Luftwaffe's ability to regenerate after losses. Bomb damage assessment focused on repair time and production disruption, rather than immediate output loss. Operational research units embedded within the 8th Air Force tracked German responses raid by raid. Fighter sortie rates, interception timing, altitude changes, and flak density were quantified to refine future missions. This feedback loop allowed bomber planners to treat German air defense as an adaptive system that could nonetheless be driven toward exhaustion. This initial conceptual decision, to define air defense as a system vulnerable to cumulative stress, shaped every subsequent American bombing tactic in Europe. It established that the objective was not survival of individual missions, but the long-term collapse of the Luftwaffe's ability to defend German airspace at all. October 14, 1943. Schweinfurt, Germany. U.S. 8th Air Force bomber formations penetrated deep into central Germany without long-range fighter escort, triggering mass interceptions that demonstrated both the vulnerability of unescorted bombers and the strategic value of compelling the Luftwaffe to commit its fighter force at scale. Losses from the Schweinfurt-Regensburg missions clarified a central problem rather than invalidating the daylight strategy. German air defenses had proven capable of inflicting unsustainable casualties only where escort coverage ended. U.S. planners concluded that extending fighter escort range, not abandoning daylight bombing, was the decisive requirement. This realization accelerated priority allocation to long-range escort development. The P-47 Thunderbolt was modified with drop tanks, but its fuel consumption limited penetration depth. The P-38 Lightning offered range, but suffered from reliability issues in European conditions. The decisive shift occurred with the arrival of the P-51 Mustang in late 1943. By early 1944, P-51 groups equipped with external tanks could escort bombers to Berlin and beyond. Escort doctrine also evolved. Fighters were no longer restricted to close bomber proximity. Instead, they were authorized to range ahead and above formations, actively seeking combat with German interceptors before coordinated attacks could form. This change directly targeted the Luftwaffe's pilot cadre. German fighter defense relied on experienced leaders to coordinate massed interceptions under centralized control. Free-ranging escorts disrupted these formations early, forcing fragmented engagements that favored numerical superiority and American pilot rotation systems. U.S. planners explicitly measured success in terms of German fighter losses rather than bomber survival alone. Bomber formations were instructed to maintain course even under attack to maximize interception opportunities. Every interception forced German fighters to expend fuel, accumulate wear, and risk destruction or damage. German industry could replace aircraft faster than it could replace trained pilots. By spring 1944, loss ratios increasingly favored the Americans. Not because German aircraft disappeared, but because veteran pilots were killed or grounded faster than replacements could be trained to operational standards. Escort fighters also attacked airfields, strafing parked aircraft and disrupting sortie generation. These actions extended the attritional effect beyond air combat into ground operations, further stressing maintenance crews and logistics units already strained by bombing. By deliberately turning bomber penetration into a continuous fighter engagement zone, U.S. forces transformed German air defense from a shield into a liability. The Luftwaffe was compelled to fight on American terms at altitudes, ranges, and frequencies that systematically degraded its ability to contest German airspace. February 20, 1944, northern France and western Germany, U.S. Army Air Forces initiated Operation Argument, later known as Big Week, launching coordinated bomber attacks designed not only to destroy aircraft factories, but to overload and disrupt the German early warning and fighter control system that directed interceptions. German air defense depended on a layered detection and command network developed earlier in the war under General Josef Kammhuber. Although the original night fighter Kammhuber line had been compromised by British countermeasures, its principles persisted in daylight defense, radar detection, centralized reporting, sector control, and vectoring fighters into bomber streams. U.S. planners recognized that even intact fighter strength was ineffective without timely detection and coordination. Radar stations along the coast and inland provided early warning, while sector control centers assigned altitude blocks and attack timing. Disrupting this process reduced interception efficiency without requiring total destruction of equipment. Beginning in late 1943 and intensifying during Big Week, bomber formations deliberately crossed known radar coverage zones to provoke responses and expose vulnerabilities. Escort fighters and fighter bombers attacked radar sites, communications lines, and control centers when feasible, forcing German controllers to operate with degraded situational awareness. Electronic countermeasures complemented physical attacks. Although more extensively used by the British, American bombers increasingly employed radar jamming and chaff to create false tracks and clutter radar screens. This forced German operators to delay fighter launches or vector units into empty airspace. The cumulative effect was a breakdown in timing. German fighters often arrived late, climbed to incorrect altitudes, or attacked from unfavorable positions. Interceptions became piecemeal rather than massed, reducing lethality against tight bomber formations. Centralized control, once a strength, became a liability under pressure. As communications failed, German commanders were forced to decentralize decisions to local units, increasing confusion and reducing coordinated defense. This shift also placed greater burden on individual pilot judgment, which was uneven among increasingly inexperienced crews. U.S. intelligence units monitored these changes closely. Interrogation of captured pilots and signals intelligence confirmed growing delays between detection and interception. Operational research showed declining engagement effectiveness even as sortie counts remained high. By early 1944, German radar and control networks were still functioning, but no longer coherent. They could detect bombers, but they could not reliably translate detection into effective interception. This erosion of command efficiency amplified the impact of escort fighters and attrition tactics already underway. The degradation of early warning and control did not destroy German air defense outright, but it stripped it of coordination. The Luftwaffe was increasingly reacting blindly, expending resources without the ability to concentrate force where it mattered. May 12, 1944. Leuna, Germany. U.S. 8th Air Force bombers struck the Leuna synthetic fuel complex, initiating a sustained campaign that directly targeted the fuel supply sustaining German fighter operations, and by extension, the operational viability of the entire air defense system. American planners had concluded that aircraft, pilots, and command systems could not function without reliable access to aviation fuel and spare parts. Synthetic fuel plants, which produced the majority of Germany's aviation gasoline, were identified as critical bottlenecks with limited redundancy and long repair times. Beginning in spring 1944, U.S. bombers repeatedly attacked major synthetic fuel facilities at Luna, Merseburg, Pulitz, Brooks, and other sites. These installations were large, fixed, and technically complex, making them vulnerable to precision bombing despite heavy defenses. Damage to cracking units, hydrogenation chambers, and power systems reduced output far beyond the immediate blast effects. The impact on German air defenses was rapid and measurable. Fighter units began receiving fuel allocations that limited training, patrols, and interception endurance. Sortie generation increasingly depended on conserving fuel for priority targets, reducing the Luftwaffe's ability to respond flexibly to bomber routes. Maintenance and logistics were simultaneously degraded. Bombing of transportation networks linked to fuel plants disrupted delivery schedules, while shortages of lubricants and replacement parts grounded otherwise intact aircraft. Engines suffered from reduced maintenance cycles, increasing mechanical failure rates during interception. U.S. operational analysis confirmed that fuel shortages produced nonlinear effects. A marginal reduction in supply translated into a disproportionate reduction in combat readiness. Fighters launched with partial loads, shortened patrol times, or remained grounded to preserve reserves. German attempts to disperse fuel production and storage proved insufficient. Smaller facilities lacked the capacity to replace lost output, while dispersed depots increased logistical complexity under continued bombing. Repair efforts were repeatedly interrupted by follow-up raids, extending downtime. By late summer 1944, German fighter units increasingly reported operational strength on paper that could not be realized in flight hours. Pilot training programs were curtailed, accelerating the decline in average experience levels. Defensive patrol patterns were simplified, making interception behavior more predictable. For U.S. bomber strategy, fuel targeting completed the transformation of German air defense into a fragile system. Fighters might still exist, but without fuel they could not train, intercept effectively, or sustain operations over time. The destruction of fuel and spare inputs ensured that losses inflicted by escort fighters and flak suppression could not be offset through regeneration. German air defenses entered a phase where each successful American raid permanently reduced future defensive capacity. June 21, 1944. Oschersleben, Germany. U.S. bombers attacked the AGO Flugzeugwerke fighter assembly plant, continuing a concentrated effort to exploit structural bottlenecks in German aircraft and engine production that directly supported the Luftwaffe's defensive mission. American targeting doctrine had evolved beyond counting destroyed airframes. Planners focused on points where production throughput could be choked despite dispersal. Fighter assembly depended on synchronized delivery of engines, instruments, landing gear, and trained labor. Disrupting any of these components slowed output regardless of intact factory buildings. Engine production proved especially vulnerable. Facilities producing the Daimler-Benz DB605 and Junkers Jumo 213 engines required precision tooling, skilled labor, and stable power supplies. Bombing of power plants, machine tools, and subcontractor workshops caused cascading delays across multiple assembly lines. U.S. bombers also targeted ball bearing plants, particularly at Schweinfurt, not because bearings were irreplaceable, but because shortages forced inefficient workarounds that reduced engine reliability and increased maintenance demands. These effects directly affected fighter availability and sortie rates. German efforts to disperse production reduced catastrophic losses but increased systemic fragility. Small workshops lacked standardization, quality control, and protection. Transportation between dispersed sites became a critical vulnerability under sustained bombing of rail networks. Operational intelligence tracked production data, repair timelines, and substitution measures. Even when monthly aircraft output numbers recovered on paper, field units reported growing discrepancies between delivered aircraft and combat-ready machines. Engines arrived incomplete, improperly tested, or lacking spare components. The interaction between production stress and fuel shortages amplified defensive collapse. New aircraft accumulated at depots without fuel for acceptance flights or pilot conversion training. Factories could not validate output, further degrading quality. American bomber routes and timing were adjusted to exploit repair cycles. Follow-up raids struck facilities during restoration phases, extending downtime and forcing Germany to allocate increasing flak and fighter resources to factory defense rather than frontline interception. By mid-1944, German air defense faced a paradox. Nominal fighter strength increased while effective defensive power declined. The system could no longer convert industrial effort into sustained aerial resistance. For U.S. bombers, this represented a decisive shift. Each mission now degraded not only current defenses, but future defensive potential. The Luftwaffe's production system, once adaptive, became a bottleneck that bomber pressure continually narrowed. August 3, 1944, Hamburg, Germany. U.S. bomber formations attacked industrial targets while deliberately altering altitude profiles and ingress routes, forcing German anti-aircraft defenses to operate outside their optimal engagement envelopes and exposing structural limitations in the flak system. German flak was organized as a dense, centralized defensive network protecting cities, factories, and transportation hubs. Heavy 88mm and 105mm batteries relied on predicted bomber tracks, stable altitude bands, and centralized fire control. Effectiveness depended on advance warning, accurate tracking, and sustained ammunition supply. American planners treated flak as a system subject to saturation and disruption, rather than as isolated gun positions. Bomber streams varied altitude, spacing, and timing to complicate fire control solutions. Small deviations imposed disproportionate computational strain on German fire direction centers. Electronic countermeasures further degraded flak accuracy. Radar-directed guns depended on Würzburg and Mannheim systems vulnerable to jamming. U.S. aircraft increasingly employed noise jamming and chaff to interfere with target tracking, forcing gunners to revert to optical methods at high altitudes. Route engineering became a primary tool. Bomber paths were selected to dilute flak concentrations, forcing German defenses to cover wider areas with finite guns. Feints and sudden course changes drew fire away from primary streams, expending ammunition without producing results. Fighter bombers and medium bombers conducted suppression attacks against flak positions, power supplies, and ammunition storage. While not eliminating flak, these actions reduced sustained fire rates during main bomber passes. Flak units faced logistical constraints exacerbated by broader bombing. Ammunition production, transportation, and crew training suffered from the same fuel and labor shortages affecting fighter units. Experienced crews were reassigned or lost, reducing accuracy. Operational data showed that flak effectiveness peaked in predictable zones. Once these zones were mapped, U.S. bombers adjusted profiles to minimize exposure time. Losses continued, but at rates insufficient to halt operations. Critically, flak did not regenerate rapidly. Guns required long manufacturing timelines, and trained crews could not be replaced quickly. Each destroyed or neutralized battery permanently reduced coverage density. By late 1944, flak remained dangerous but increasingly inefficient. It imposed costs without delivering decisive attrition. Combined with degraded fighter response, flak could no longer function as a standalone defense. The systematic neutralization of flak completed the erosion of Germany's integrated air defense. What remained were isolated defensive elements unable to compensate for the collapse of the system as a whole. March 18th in 1945, Central Germany, U.S. bomber forces conducted large-scale daylight operations encountering limited, uncoordinated fighter opposition, marking the effective failure of Germany's integrated air defense system to contest American air superiority. By this stage, the breakdown was not attributable to any single loss or campaign. It was the cumulative result of sustained pressure applied across every functional layer of German air defense. Early warning still detected bomber formations, but detection no longer translated into timely interception or concentrated fire. Fighter units existed in fragmented condition. Aircraft were available in depots and on airfields, but fuel shortages, pilot inexperience, and maintenance deficiencies prevented sustained operations. Interceptions, when they occurred, were brief, disorganized, and tactically ineffective. Command and control structures were hollowed out. Centralized direction had collapsed under repeated disruption. while decentralized units lacked the situational awareness and leadership to mount coordinated responses. Communications failures and fuel rationing further constrained initiative. Flak concentrations remained around key locations, but could not compensate for absent fighter cover. Ammunition shortages and degraded fire control limited effectiveness. Guns fired, but without the density or accuracy required to impose prohibitive losses. Industrial regeneration was no longer possible. Aircraft and engine production, though still functioning in reduced form, could not translate output into combat power. Repair cycles were interrupted faster than they could be completed. Training pipelines produced pilots without sufficient hours to survive modern air combat. U.S. bombers now operated with strategic freedom. Routes were chosen for operational efficiency rather than defensive avoidance. Escort fighters focused on ground attack and airfield suppression rather than bomber protection alone, further reducing any residual defensive capacity. The German air defense system had entered irreversible decline. Each American operation reduced not just current resistance but the possibility of recovery. The system lacked the fuel, manpower, coordination, and industrial depth required to regenerate under continuous attack. This outcome validated the original American concept. Air defense could be treated as a system vulnerable to sustained, targeted pressure. By forcing German defenses to respond repeatedly while denying recovery, U.S. bombers systematically dismantled the mechanisms that once protected German airspace. The collapse of German air defense was not sudden. It was engineered through cumulative decisions, precise targeting, and deliberate exploitation of systemic weaknesses. By 1945, the system no longer functioned as a defense at all.